talking about noise. Now we're going to talk about noise, and to be able to discuss noise and make sure that we make sense of the whole process, there are some mathematics that we'll need to quickly review, and there's some physics. So we'll do the mathematics right now and do the physics probably next time. So this is basically the mathematics of noise. So we are thinking about noise, or more accurately, if you have stochastic processes. So what's the thing about stochastic process? So think about a resistor in our terms. A resistor, if you look at the voltage across the resistor, you will see that it's not constant, even if it's not attached to anything. If it's that jump temperature above 0 Kelvin, you will see that it has some variations. So you see some voltage that changes with time. If you look at it carefully, you will see some random looking thing versus time. Now, this is a random process. You don't know what the value of this thing is at any point in time. It's, for all intents and purposes, as far as we are concerned, random. It's unpredictable, the exact value. But there are still some statistical properties of it that we can talk about and characterize it. You can clearly see that this one, if I take another resistor of exactly the same value, so let's say if this is 1 ohm, this is exactly 1 ohm. And look at the voltage of that over the same time period. Will I see the same voltage? No. I see something else. And if I take another one, I'll see different things. So let's think about R, these resistors R. If you have N of these resistors, each one of them gives you a different property. Now keep in mind, they all have the same value, but each one of them generates different values in time or versus the resistance. Now, there are different things. We call this an ensemble, right? So if I say, what is the ensemble average of this thing? What is the statistic? The average of this thing. Is this positive, negative, 0? What I mean is that I look at a large number of these samples, of these resistors, right? Let's say at this point, and I look at it and say, well, okay, what is the value here, what's the value here, what's the value here? I add these values, I divide them by the number, and as n goes to infinity, that should give me the ensemble average. That's the meaning of an ensemble average. Now, there's another kind of average that we can define. We can define a time average. We can look at it over time in this direction. And in general, these moments, in particular the average is the first moment, or 0th order moment, do not have to be, or the first order moment, I'm sorry, do not have to be equal. Now, if they are equal, basically we call this a process an ergodic process, where we can replace the statistical averages, the ensemble averages, with time domain averages. So, how do we define a time domain average? How do we define a power for this? If you were looking at a periodic signal, let's say some periodic signal, how would you define its power? If I wanted to define the power of this periodic signal, how would you define it? Let's say it's a voltage. Let's say this was a voltage, V of t. What is the average power of this thing? So how do we define it?
The average of the square.
Or let's say this is a voltage across a resistor. So we say the instantaneous power is V squared of t over R. Right? And what we do, we say, okay, we look at it over one period. So let's say this is one period, t. And we say integrate it from, well, let's say this is centered around 0, it doesn't matter. V of t squared over R dt. Normalized by t. This is the average power of this thing. And this is what we call RMS. So in general, if I had a quantity x of t of this kind, the average power of x of t for a periodic signal would be minus 1 over t, integrating it over one period, x squared of t dt. Which we can show like this. Because what we're doing is we're really averaging the x squared. It's a mean squared average. Right? So now, but that's a periodic signal. How about noise? Noise is not periodic. And so, can we generalize this definition in a meaningful way? Well, think about noise. duration of the entire universe. You can't prove that it's not going to repeat exactly the same way, right? So I can think of it as a periodic signal with a very long period, for all intents and purposes. So that's why, for something like this, the average power of noise, if you have this as x of t, then becomes the limit of t going to infinity of the same thing. So I'm assuming that it has an infinitely long period. I can think of it as an infinitely long period being repeated multiple times. So this is the definition I use for moment. So if I wanted to look at the average of the power, look at that. If I wanted to actually look at the basic average, I would look at the same thing. So if I wanted, this is the power. If I wanted to look at the average, I would do the same thing over x. So I can define lower and higher order moments this way. Okay? So this is, there's nothing magical about it. So now if x, the quantity x is a voltage, to get the actual power, if I have a v squared like that, I have to divide it by r. If it's a current, to get an actual watt kind of power, I have to multiply it by r. The resistor across which disappears. Fine. So that's the basic thing. Now, the question is, these quantities are fine, but this is like some sort of an average. It doesn't tell you anything about the frequency content, how it changes. Is it like high frequency, low frequency? How can we generalize this to another concept which is a more informative concept? So let's say you have a source, let's say a resistor or whatever. Then the question is, how can I determine, or let's say generally a power source? I want to know what is the power spectrum of this thing. In other words, I want to see how the power is distributed across different frequencies. Is it high frequency, low frequency, and etc. How do I do that? Well, okay. So the fundamental definition of what we call the power spectral density is what I'm going to show you. And I'm going to tell you what it's related to. So what you do, if you were to do it in the lab, at least some sort of an semi-thought experiment, is that what you do, you make a filter. You make a bandpass. If you had an ideal bandpass filter, let's say, with a bandwidth of, let's say, 1 hertz, at center frequency f1. You take that, and then you put it into a power detector. Let's say a power detector or something like that. And measure this power. And then you plot it versus frequency. So for f1, you say at f1, only power at around within 1 hertz of f1 will go through and nothing else goes through. So I measure some power. And then if let's say I can move the center frequency of this filter, I can change it. At f2, I measure this is f1, f2, f3. I measure it at different frequencies. And if I plot this quantity, this is defined, this is the fundamental definition of the power spectral density. This is the most fundamental definition of power spectral density. Now, you can show mathematically that this is related to autocorrelation function. And I'll tell you what the autocorrelation function is. Now, autocorrelation, you think about the averages that we defined. You remember this average? Let's say we said this is the power of the signal. But this only looks at the value of signal at a given time at any point and multiplies it by itself. So it says at this point what it is, multiplied by itself, just square it, and then average this. What if I wanted to get more information? I have to not only look at the signal times itself at that point, I have to, if I look at the signal times signals at other times, I get more information, right? Because it tells me it already has the information about the signal times itself here, but it also gives me information about how it changes over time. So is there a large correlation, for instance, to a later time or not? Or is there any correlation? So you can actually modify this definition to get the autocorrelation. So the way you can modify it, say, well, instead of looking at the signal squared, I basically define this as the same integral over x of t and x of t plus tau et. So I multiply the signal at this x of t and multiply t plus tau, and look at this value. So this gives me a function that becomes a function of tau. In general, this is a function of t and tau, because it could be different at different times. This depends. But if the process is time invariant, basically we call it stationary in terms of stochastic processes. Stationary means that if I do it between these two times, I should get the same result as if I kept the same time distance and moved it here and looked at it like this. No matter where I look at this time difference, statistically I get the same thing. So this is called autocorrelation of the signal. So that it's shown with R sub XX of tau. And you can imagine if you can basically define a cross correlation of X and Y. So what is X, the other one is Y, becomes RX Y of tau. It tells you something about the correlation of two signals. But now, if you define this autocorrelation function, what you can mathematically show, so autocorrelation function is defined like this. For signal X, Rx X of tau is defined as the limit of t going to infinity, 1 over t, integral t minus t over 2 plus t over 2, x of t plus tau, dt. And for a stationary process, it would not be a function of t. So this is what you get. Now, mathematically, you can prove. So this is something you can prove. This is not a definition of spectrum, power spectrum. Mathematically, you can prove that S, x of f, the power spectral density of a signal, is the Fourier transform of the autocorrelation function. So this is not a definition. That's not the definition. This is the definition. Really. This can be proved. And if you're interested, I can give you a reference for it. Let's look for that. So if you define it that way, you can prove this. Now, this is important because what it tells you is that essentially it's the Fourier transform, which basically, by the way, the Fourier transform is integral from minus infinity to plus infinity of Rx x of t e to the minus j2 pi tf dt. So that's the Fourier transform. So that's how they relate. Now, there's another property which is even more important mathematically, and the basis of a lot of the analysis that we do. So let's say you have an LTI system, linear time invariant system. It's an LTI system whose inputs, let's say x of t, and output y of t. You can characterize an LTI system with what? With its impulse response, h of t. Or in frequency domain, using its transfer function, which is the Fourier transform of the impulse response, right? We've talked about it before. H of j over f. Right? So you can define it in terms of, in time domain or frequency domain. So in frequency domain, basically, if you have x of f or x of s in general, you have y of s and h of s. So we knew that y of t was x of t convolved with h of t, which basically is defined as the integral of minus infinity to plus infinity, x of t, h of t minus tau, well, t prime, let's say. T minus t prime, dt prime, convolution. And in frequency domain, we knew that y of s is basically h of s times x of s. But these are for deterministic signals, right? We said you can define these things as what is x of s for a sine wave, you know what it is. But for whatever periodic signal, you know. If it's an aperiodic, it's deterministic, you know. It's the Fourier transform of that signal, or the Laplace transform in general, which is the generalized form of Fourier transform. What if these signals are stochastic? What can you say? Now, instead of x of s or x of f, what if I know the power spectrum of x, or I know the autocorrelation function of x? If you have stochastic properties, you can't say what the signal actually is. You can look at the sample of the signal and say, for this sample useful because next time you won't get that sample, you get a different sample. But what you know about it is that you can define an autocorrelation function, which basically whose Fourier transform would be the power spectral density, PSD. So I want to know if I know the autocorrelation or the power spectral density of the input signal, what is the autocorrelation of the output signal? Or SY. So how are these related to each other? And this is a very important thing. It's a simple thing. It's a very useful thing because it allows us to use the transfer functions that we've calculated to determine the behavior of the node. So what does it tell you? So it turns out that you can show this is trivial. You just use the definition of the autocorrelation function and put the convolution in there, and you will see that there are three integrals that basically just switch order. And then you switch the order of the integrations, and there's a simple change of variables. And when you do that, you will see that RYY of t is Rxx of t convolved with h of t convolved with h of minus t. So if you know the impulse response of the system, you can actually, if you know the autocorrelation of the input of an LTI system, you can determine the autocorrelation of the output. This is very useful. Now, even more useful than that is when you take the Fourier transform on both sides. If you take the Fourier transform on this side, you get Sy of f. So the power spectral density of the output becomes the power spectral density of the input. Remember, Fourier transform, in Fourier transform, the convolutions become multiplications. Multiplied by h of s, or let's say h of f, times, and this, it gives you h star of f, complex time. Which basically is saying the power spectral density of the output is the power spectral density of the input times the magnitude squared of the transfer function at that sequence. So, if you know the transfer function for a signal from an input to the output, for a deterministic signal, if you know your impulse response or the transfer function frequency domain, that's enough to know what comes out for a given source. If you have the properties of that source, oh, this is x. If you know the power spectral density of that source or its autocorrelation function, you can determine that. But then, of course, if you know one, you know the other, right? If you know the autocorrelation function, you do a Fourier transform to get this. If you know this one, you can do an inverse Fourier transform to get that. So this is actually pretty useful because it allows you to evaluate the system. So for instance, if I have a input source that's white noise. White noise is basically flat. It doesn't have any dependence on frequency. So its power spectral density is a constant. Right? What happens? What comes out? If you have this as your input, and let's say your system is a bandpass system with this kind of transfer function. It basically shapes your noise, the output, in this form. So if you look at it on a spectrum analyzer, which basically shows its power spectral densities, you will see that it will be shaped. This is in fact one way to evaluate the transfer function of systems. If you have systems whose transfer functions can be very complex and they may have, if you want to guarantee that there are no arbitrary peaking or notches or things of that sort, one of the ways to do that is basically by noise. You just put a large noise source into the system and look at the output. And that way you evaluate all frequencies at once, essentially. And you see if there's not any hidden thing as opposed to sweeping a sinusoid where you can miss something that's very sharp. So that's very important. And that's the basis of all of our analysis for noise analysis. So that we do. A lot of times what we do the transfer function. Because we know how to determine the transfer functions, right? We spend a fair amount of time looking at methods of time constants, etc., to determine the transfer function. So now that we know how to determine the transfer function, and now then what we do next when we talk about the physics of noise is we determine the properties, the power spectral densities of different noise sources. So we know the properties and power spectral densities of sources. We know the transfer function. We can calculate the transfer function from the sources to the output. Therefore, we can determine what's the power spectral density and the statistical properties of the node at the output. And that's what we do. Now, there's another thing. So this is for one source. What if you have two sources? and x2. So this is one noise source, this is another noise source. Right. And let's say you add them. So you get x1 plus x2. What can you say about the statistical properties? So we have two noise sources, x1 and x2. We're adding them to get the sum of the two. So what can you say about the statistical properties? So let's first talk about the average. x1 plus x2 average. From the definition you can see that basically it's that integral, right? Evaluated from minus infinity to infinity, and then you can basically the sum of the two integrals. So you basically get x1 plus x2, the sum of the averages. Now, how about their power? So what you really need to evaluate is this, right? What is that? Well, it's the integral of limit of t going to infinity of 1 over t of x1 plus x2 squared dt, right? Since I'm lazy, I don't want to do all of this again. I just expand it here again. Right? So let's expand it. So instead, I can write it as x1 squared plus x2 squared plus 2x1 x2 dt. And that gives me three integrals. I should factor this limit. Okay, the limit or whatever. The integral, the same limits. Times that dt. So what is this? This is the power of x1. What is this? The power of x2. What is this? This is the 2 times x1, x2 average. Just a cross power. It's called the cross correlation term. So now, if these two are independent, completely independent, what can you say about x1 and x2? So are uncorrelated. So x1 and x2, statistically over a long period of time, cancel each other out. If they're zero mean, essentially, there have to be zero mean for that to happen. So for uncorrelated signals, then this becomes x1 squared plus x2 squared. So it means that the total power of, let's say, y for an uncorrelated source is the sum of the powers. So if two sources are uncorrelated, what happens is that the powers add. Now, what if they're correlated? Then this term becomes, let's say they're fully correlated. Then this term basically is twice as significant as these guys, so it's basically the power of the sum squared. So to give you guys a sense of correlated versus uncorrelated, what does it mean to be correlated, what does it mean to be uncorrelated? Let's run a little experiment. I want everyone to think of your favorite one-digit number in your head. We'll say it. On the count of 3, I want you to shout it out loud. Okay? 1, 2, 3.
2.
Okay. You see? So now I want everyone to say my favorite number. Say 5 on the count of 3. Right? 1, 2, 3.
5.
See? That's the difference between correlated and uncorrelated. The first one, you added in power. So you kind of like cancel each other out on the average. You didn't not completely, but you didn't add as much. But when you did the 5, the second time, you all said the same thing. So that was a correlated source. So you get a lot more signal. You add in amplitude as opposed to add in power. So that's important when you discuss different sources of noise, and we'll talk about that later. Okay, so let me stop here. And next time we'll talk